Hello, everyone. Hope you all are doing well. Welcome to the second day of the symposium. This is the session number 5.3. And before we get started, I would like to remind you that we have a limited time. So in order to finish our session in time, you should finish your presentation within 10 minutes, at most 12 minutes. Thank you. So we can start based on the list I have. The first author is Diego Alonso. Are you here, Diego?
Yes, I'm present.
Okay. You can share your screen.
This is our PPT. Can I start now?
Yeah, you can start.
Okay. I can open my video camera or just like that.
No need to camera.
It's not necessary.
It's not necessary. You can start.
Oh, I can start. Okay. Thank you. Okay. Good morning, everyone. My name is Diego Bejarano, and on behalf of my co-authors from the Technological University of Peru, I'm honored to present our technical review. Phishing detection framework and cybersecurity effectiveness during the COVID-19 pandemic. Next slide, please. We begin with the introduction. Phishing is one of the most persistent threats in cybersecurity, characterized by its use of social engineering, cunning, and manipulation to illicitly obtain confidential information. During the COVID-19 pandemic, this threat reached unprecedented levels. As our lives moved online, phishing attacks increased by an alarming 220%. Next slide, please. Cybercriminals exploited the global crisis, crafting sophisticated campaigns around health topics and financial aid to deceive vulnerable users. While many advanced detection frameworks were developed, we identified a critical gap in the existing research. Previous reviews remained confined to traditional methods like blacklists and static signatures. There was a clear need to access advanced machine learning techniques. We found that even with these new frameworks, their performance in real-world environments was uneven, showing limitations against new attack variants and suffering from a lack of standard evaluation metrics. Therefore, the objective of our systematic literature review is to analyze the advances, limitations, and effectiveness of phishing detection frameworks used during the pandemic, evaluating their adaptability to new tactics and their efficiency in remote work environments. Next slide, please. To guide our research, we first employed the Peacock methodology. This allowed us to structure our central research question. How did phishing detection frameworks show effectiveness during the COVID-19 pandemic? We broke this down into 5 key components to explore the topic in depth. Population, the exposure of users to phishing attacks during the pandemic. Intervention, the use of phishing detection frameworks. Comparison, the differences between various frameworks in terms of performance. Outcome, measuring the effectiveness of phishing detection. Context, the unique environment of the COVID-19 pandemic. From this question, we identified keywords like machine learning, detection accuracy, and remote remote world phishing attacks to build our search equation. Next slide, please. This led us to the Prisma methodology for our literature selection. We began with 40 articles identified from the Scopus database. We then applied very specific inclusion and exclusion criteria. For example, we excluded studies based solely on blacklists, those lacking quantitative efficacy metrics, and theoretical proposals without empirical validation. After this rigorous process of removing duplicates and evaluating eligibility, only 20 studies met all requirements and were included in our final analysis. Next slide, please. Now we'll talk about results. I'll present the key findings from our analysis structured around our 5 research questions. Next slide, please. First of all, how did cybersecurity issues arise or increase during the pandemic? Our research shows it was a perfect storm. Attackers exploited public fear with campaigns about vaccines and economic aid. The abrupt transition to remote work exposed flaws like insecure home networks and weak authentication protocols. As you can see in the chart, this was driven by key factors. 65% from new system vulnerabilities, 52% from accelerated digitalization of services, and 30% from lack of digital awareness. Next slide, please. Second and third, how do framework prevent attacks and what are their difference in accuracy? The most effective frameworks integrated multiple techniques, such as automatic pattern selection and malicious URL analysis. Our findings reveal a significant performance gap. As this graph illustrates, models based on machine learning achieve outstanding results. Random forests achieve 1990.78% accuracy and k-nearest neighbor reaches 99.67%. This is a massive improvement over traditional non-machine learning methods, which typically have an accuracy between only 70 to 85%. Next slide, please. And this is what difference are there between the frameworks in terms of their effectiveness and accuracy. We have all the frameworks that we analyze in the paper. Next slide, please. And now, what has been their effectiveness in terms of phishing detection? We found that different models excel at different tasks. Machine learning models like XGBoost and Random Forest were the most effective against large-scale attacks due to their speed and high performance. On the other hand, hybrid and deep learning models, which use neural networks like LSTM and CNN, were superior at identifying new topics, that is, novel phishing campaigns that exploit emerging events. As the graph shows, hybrids score highest on new topics, while machine learning dominated large-scale attacks. Next slide, please. Finally, how did phishing attacks affect the pandemic context? The impact was severe. Attacks evolved from sporadic threats into massive coordinated campaigns. We classified this impact into 4 critical dimensions: human vulnerability, economic impact, innovation in attack methods, and the targeting of vulnerable sectors. On the point of innovation, attackers used polymorphic techniques and widely distributed phishing kits. which made it easier for even unskilled individuals to launch attacks. As the chart clearly shows, attackers strategically targeted the most critical sectors. Uh, the, the healthcare sector was the primary target, absorbing 50% of attacks, with criminals seeking patient data and disrupting operations. The financial sector was next, with 35% focused on identified theft, and the government sector received 15% of attacks. Next slide, please. Okay, now we'll talk about the discussion. This brings me to our discussion. Our findings reveal a critical paradox. On one hand, AI-based frameworks like random forests have demonstrated near-perfect technical accuracy, over 90% in controlled tests. However, this high performance did not fully translate into real-world effectiveness. In critical sectors, factors such as poor staff training, the rushed digitalization of processes, and the sophistications of targeted attacks significantly reduce their practical effectiveness. In fact, 65% of successful attacks used messages appealing to the health emergency, proving that the human element remains the most critical vulnerability. Next slide, please. In conclusion, this systematic review allows us to evaluate the effectiveness of phishing detection frameworks, fulfilling our main objective. The results confirm that machine learning-based frameworks significantly outperform traditional methods, reaching accuracies over 90%. However, the study also reveals their most significant limitation, a gap between technical precision and a real-world implementation. We found that technology alone is not enough. The problem must be addressed with a comprehensive perspective that combines technical solutions with human and organizational components. Next slide. Next slide, please. Based on our findings, our future goal will be to design a new hybrid framework. This framework will combine high accuracy models like random forest and LSTM with modules specifically designed for social engineering detection. We will then validate this model in a simulated real-world environment against attacks that exploit human behavior to finally address the critical gaps we have identified in this research. Next slide. Thank you for your attention, and I am now happy to answer any question you may have.
For your presentation. Any questions? Probably no questions. Thank you again. So we can proceed to the next one. The next study is paper ID 70. Dimitar Manko, are you here? Dimitar is not here. Yuan Shi Mao, are you here? Not here. So we can continue with Mert Hayar. Mert.
Hello, I am here.
Okay, you can start.
Okay. Okay, is it clear? Can you see my presentation?
Yes, yeah, it is visible. We
Okay,
can
thank
start.
you. Hello everyone, I am Mert Hayar, and in this study I will present a crop recommendation system developed using smooth enhanced machine learning models to support smart agriculture applications. The project was conducted at Istanbul Kültür University, and our primary goal is to improve agricultural productivity and contribute to global food security. The presentation covers the importance of crop recommendation systems, dataset characteristic, data pre-processing stages, the SMOT technique, the machine learning algorithms used, correlation and confusion matrices, simulation results, and the future directions of this study. Agriculture is essential to meet the food requirements of the growing world population. The research done by United Nations highlighted that the global population will reach around 10 billion by 2050s. And even today, nearly 30% of the world's population lacks adequate access to food. Climate change is one of the major factors reducing agricultural productivity. Therefore, digitalization and data-driven decision-making have become essential in modern agriculture. The main goal of the crop recommendation systems is to support this digital transformation and increase productivity. Crop recommendation systems help farmers identify the most suitable crop according to soil and climate conditions. These systems analyze environmental parameters such as soil elements levels, pH values, temperature, and rainfall to make more accurate decision making. This leads to increased productivity, reduced resource waste, and support sustainable farming practices. In this study, we have merged two open access datasets by using data mining techniques and created one original dataset. The created dataset contains total of 2,534 samples. The table on the right side shows the number of the samples in each of the 11 crop classes. Also, when we see the table, and we can say that the data distribution between the crops are unbalanced. For example, cotton has 750 samples, whereas crops like apple, banana, and coffee each have only 100 samples. This imbalance causes machine learning models to learn the majority classes more than the minority classes. The issue is known as the class imbalance problem in the literature and leads to high bias, low recall, and inconsistent performance. To solve that issue, oversampling techniques becomes essential. Before applying machine learning algorithms, we had to apply some data pre-processing steps. Firstly, missing and inconsistent records were removed, then feature scaling was applied. And finally, the most critical issue, the class imbalance was identified. To address this problem, we had to use smooth oversampling technique to balance our dataset. Smooth is one of our main topic in this study. As we know, it generates synthetic samples for minority classes. And this technique expanded our dataset from 2,534 to the 8,250 samples, with balancing each class at 750 samples. As a result, all models were trained on fair and balanced data, and the results clearly demonstrate that Smooth significantly improved overall performance. In this study, we have used 4 machine learning algorithms, and these are multilayer perception, key nearest neighbors, decision tree, and random forest. We have chosen these algorithms because the previous studies have shown that they perform well in classification problems. Also, the dataset we have created is a classification-based dataset, which makes these models a good fit for our study. Performance evaluation was conducted using accuracy, precision, recall, F1 score, random mean square error, and mean absolute error. Additionally, key-fold cross-validation was applied to ensure the reliability of the results. Let's continue with the correlation matrices. The left matrix shows us the correlations before oversampling, and the right one shows the correlations after smooth. The general correlation structure remains preserved, although a slight weakening can be observed in some relations. This is expected because Smooth increases data diversity by interpolating within the feature space. But importantly, it does not distort the original data distortion. Let's continue with the confusion matrix. This table shows the classification results of the random forest model before SMOT was applied. The reason I present the confusion matrix of the random forest method is that it achieved the highest performance among all models. Even without oversampling, random forest algorithm demonstrated balanced performance between classes, but here the main problem is that the classes are not equally represented. After applying SMOT, the diagonal becomes almost fully populated, and the meaning that model accurately predicts nearly all classes. Only few minor errors remain. This clearly demonstrates that SMOT resolves class imbalance and significantly improves generalization. Since all classes are now equally represented, the model learns each crop fairly. And these two tables shows us the simulation results of our machine learning algorithms. Before the SMOT, the performance gap between models was substantial. Decision tree and random forest performed relatively well while MLP struggled due to imbalanced data. Also, the KNN achieved moderate performance. After SMOT, all four models show a dramatic performance increase. Decision tree, random forest, and KNN exceed 99% accuracy, and MLP rises to approximately 90%. These results show that SMOT improves not only accuracy but also precision, recall, and F1 score across all models. In this page, I will show you key fault effects. Without oversampling, key fault results shows clear instability. MLP fluctuates significantly across faults, and although KNN, decision tree, and random forest are more stable, they still cannot reach their best accuracy levels. This is because each fault contains a different distribution of imbalanced dataset. After SMOT, all models reach high accuracy levels and the inconsistency between faults disappears. Random forest and KNN exceed 99% while MLP stabilizes around 90%. This indicates that SMOT enhances not only performance but also stability and generalization. In order to conclude our study, it demonstrates that machine learning models trained on SMOT balanced dataset achieve highly successful results in crop recommendation systems. Tree-based models, particularly random forest and decision tree, achieve high accuracy and low error rates. This approach provides a strong decision support mechanism that enhances productivity and supports sustainable agricultural applications. About the future works we can apply to this study, incorporating additional environmental attributes like humidity of the air or humidity of the soil, expanding dataset diversity, experimenting with different type oversampling techniques, and developing a real-time decision support system powered by IoT sensors. Thank you for listening. I will be happy to answer your questions if you have.
For your presentation. Any questions to be asked? No question, thank you.
You're welcome.
So we can move on to the next one. Ali Berkol.
Yes, I'm here.
Okay, you can start.
Okay. Can you see my screen?
Yes.
Okay. May I start?
Sure, of course.
Okay, thank you. Good morning, everyone. My name is Ali Berkol, and today I will present our study on applying genetic algorithms for hyperparameter optimization in deep learning models. The main idea is the simple but powerful. Instead of instead of testing every possible configuration, we let an evolution algorithm discover the best training parameters automatically. We want to save both time and computational resources. So selecting parameters such as learning rate or batch size has a huge impact on the final model. As you know, by using these parameters in assessment in some kind of defense industry applications, we just start to use the traditional methods like grid search for the test every combination. That's accurate but extremely expensive. So random search is faster, but it's like throwing darts in the dark. So we need an adaptive mechanism that learns from previous trials. That's exactly what generative algorithms offer. Now, our search had three key goals. First, to build a complete genetic algorithm-based optimization pipeline for deep learning models. Second, to verify its performance on a standard dataset, as you see in MNIST. So finally, to benchmark it against existing search strategies, showing how genetic algorithm improves both accuracy and efficiency. The literature provides several optimization techniques, as all you know, the Bayesian, the particle swarm optimization, and even differential evolution. So, however, genetic algorithms remain one of the most important because they balance exploration and exploitation. So they can escape local minima and adapt to different search landscapes, which is ideal for deep learning's complex parameter spaces. As all you know, a genetic algorithm is a natural evolution. So we start with a population of random hyperparameter sets. Through selection, we keep the best individuals through crossover and mutation. And we create new candidates. So over generations, the population evolves actually towards the better accuracy. So the effectively learning how to train the model more efficiently. So each chromosome represents a possible configuration of hyperparameters in deep learning. So by encoding them into a simple vector, genetic algorithm can easily manipulate and recombine these parameters just like genes. So this, as you see, this kind of a design, as you see on the screen, allows continuous and discrete variables to coexist, making the algorithm flexible for different model types. Actually, as you see, it's a pseudocode and it summarizes the core workflow of our genetic algorithm-based optimization process. Of course, we start by generating an initial population of random hyperparameter sets. So each chromosome represents a unique model configuration, including learning rate, batch size, number of epochs, and optimizer type. So for each generation, we train the model for every chromosome and calculate its validation accuracy, which serves as the fitness value. So the best performing individuals are selected as parents, and new offspring are produced using crossover and mutation to maintain diversity and avoid early convergence. So this evolutionary cycle repeats until we reach a predefined number of generations or converge is observed. So finally, the algorithm returns the chromosome with the highest fitness, representing the optimal hyperparameter configuration. So essentially, this approach enables the model to evolve towards better performance, means learning how to learn through guided exploration. So we implemented the framework in, as you see on the Python 3.11, using TensorFlow and Keras. So as we talked, our dataset is MNAST, as you see in 60K for training, 10K for test. So the model itself is a lightweight convolutional neural network because we want to go this kind of algorithms to in edge AI. So enough to show meaningful accuracy differences while keeping the computational load practical. So each candidate configuration trains the same convolutional neural network with its own parameters. and the fitness equals validation accuracy. So that way, genetic algorithm directly optimizes what matters most. So the baseline methods use the same search space and stopping rules, ensuring a fair comparison of efficiency and performance. Now, as you see in our figure, the genetic algorithm continuously improves the model's validation accuracy over generations by the nature of genetic algorithm. So we can clearly observe a steady convergence trend indicating that the genetic algorithm effectively balances exploration and exploitation in the search space. So now if we look at the table, we can see the proposed genetic algorithm achieved the highest validation accuracy of 99.2. So it outperforming both random search at 98.7 and grid search is 98.5. So when is even more important is efficiency. Genetic algorithm reached this result using only 60 evolutions, 60 epochs actually, while random search required it in 100 and grid search is 121. So this shows us that genetic algorithm not only produces better results, but it also saves computational costs and reduces training time, actually, which is crucial for real-world deep learning applications. So the genetic algorithm consistently outperforms traditional methods in both accuracy and cost effectiveness. So beyond the numbers, genetic algorithm proved to be robust. So it doesn't get stuck in local minima easily. So the mutation keeps diversity alive and avoiding premature convergence. So these qualities makes genetic algorithm especially valuable in resource constraint or some kind of real-time systems such as defense or embedded AI applications. So to conclude, our results confirm that genetic algorithms can efficiently tune deep learning models while maintaining the interpretability. So looking ahead, we plan to extend this framework to multi-objective optimization, balancing accuracy and computational cost. Also, we also aim to apply it to real-world data sets, especially in our radar defense systems and embedded AI systems where every second of training matters. Thank you for listening.
Thank you for your presentation again. Any questions for this study? Be asked. Okay, no question. Thank you again.
Thank you.
So our next study is of Altan Konuk.
Yes,
Are you here?
I am here and sharing my screen.
Okay, we're waiting for your study.
You can see my screen, right? No
Yes,
problem.
yeah, you can start.
I am about to present our study titled The Impact of Digitalization of Operational Efficiency Import, a case study of Borusan Port. This study was conducted in collaboration with Professor Dr. İbrahim Çil from Sakarya University and Kazım Alper Konuk, the maintenance and technical manager at Borusan Port. Ports today face unprecedented load due to global trade growth. They must manage large volumes of cargo, tight operational windows, and multi-actor coordination. Traditional operations still rely heavily on paper-based procedures, manual communication, and fragmented information flows, causing insufficiencies such as cargo delays, misallocation of resources, and safety risks. In literature, ports that fail to integrate digital technologies experience higher operational bottlenecks, slower decision-making, and reduced competitiveness. The absence of real-time data flow leads to delay in container handling, gate congestion, and inefficient equipment utilization. In this context, digitalization is seen as the key enabler that integrates stakeholders, eliminate manual dependencies, enhance monitoring accuracy, and support the shift from reactive to predictive operations. With this background, let us move to primary research question that guided our study. This study seeks to answer the following central question. How does digitalization improve operational efficiency, occupational safety, and coordination in port operations? And what practical insight can be drawn from the Borusan port case? To address this question, our study combines literature analysis with real operational data obtained from Borusan port. We examine efficiency indicators such as real-time personnel monitoring, heavy equipment tracking, collision avoidance, and automated task assignment. Before diving into technological aspects, it is essential to understand how port digitalization has evolved historically. Therefore, I will now explain the three generations of digital transformation defined in the literature. Port digitalization can be grouped into three major generations. First generations transition to paperless process through AD systems. Port adapted reservation billing and accounting systems. Terminal operating systems began integrating basic tasks. Second generation introduction of automation. Post-delayed sensors, laser systems, automatic identification systems, and track operating systems. Third generation smart ports. Comprehensive IoT networks, real-time data fusion, advanced analytics, and centralized decision centers. These generations highlight the increasing role of connectivity, automation, and real-time data in modern port operations. Based on this, let us review two key digital technologies used globally and at Borusan Port. GNSS DGPS provides high precision positioning of vehicles, cranes, and AGVs, especially important in automated terminals. RFID used for electronic seals, container tracking, gate automation, truck driver verification, and access control. OCR automatically recognize container IDs, license plates, and damage patterns. RTLS enables continuous indoor outdoor tracking independent of satellite signals. These technologies provide the infrastructure needed for real-time operations, which bring us to the focus of this study, Borsan Port and its ongoing digital transformation. Borsan Port is one of the Turkey's most strategically positioned and technologically advanced ports and is a regional logistic hub for South Marmara, North Aegean, and Western Anatolia. Its large-scale operations and diverse cargo profiles necessitate a highly reliable and transparent digital infrastructure. Next, I will walk you through the step of the port's digitalization journey. Borusan Port digital transformation began with the integration of Navis Spark M4 and BobSnet, enabling real-time operational visibility and centralized workflow management. Key milestones include launch of customer-facing digital platforms, advanced storage system with 3D addressing, automation of labor-intensive areas, real-time IoT-based task and personnel tracking. To understand how these components work together, let us examine the system architecture. The system architecture is built on four software layers and multiple hardware layers. Personnel tasks generate real-time location data every 5-10 seconds. UVB RF anchors receive signals and relay them to the gateway devices. Gateway transfer process data to central servers through Ethernet or GSM. The central engine calculates positions, trigger alarms, store historical data, and feed dashboards and mobile apps. The architecture supports features such as emergency alarms, fall detection, mobile notifications, central monitoring screens, and 1-year historical data storage even if devices are replaced. Let us now review the hardware structure that makes this architecture possible. Borsamport deployed 7 complementary hardware devices. Mobile personnel device, anchor devices, Ethernet-based gateway, vehicle tracking device, collision warning device, relay-enabled anchors, central control unit. These devices together form a highly detailed and reliable monitoring ecosystem. Next, I will explain the outputs produced by this system. The system produces a wide range of operational, analytical, and safety-related outputs. Real-time map monitoring with department-based color coding. Heat maps visualizing frequent movement areas of personnel and heavy equipment. Vehicle dashboards showing distance traveled, working hours, engine activity, and speed time relationships. Zone-based reports showing personnel and equipment density. Violation reports documenting hazardous proximities. Contact tracing reports analyzing interaction changes. Shift reports identifying missing or inactive personnel. CAN bus reports for engine diagnostics. Mobile notification and task assignments. These outposts transform raw location data into actionable intelligence. Based on these findings, let us examine the improvements observed. Key outcome observed at Borusan Port. Operational transparency significantly increased due to real-time monitoring. Unsafe behaviors and proximity risks were reduced through instance alerts. Resource allocation became more efficient thanks to detailed equipment usage data. Engine hours, speed profiles, and driver behaviors analytics help optimize fuel usage and maintenance plans. Personnel movements across virtual zones enabled workflow optimization. Restricted area alarms strengthened safety compliance. Automated data collection reduced the need for manual reporting. Overall, the system improved efficiency, safety, coordination, and decision-making capabilities in the port environment. Finally, let us look at the future development areas. This study demonstrates that digital transformation at Borusan Port supports both operational performance and safety. The IoT-based architecture provides the foundation for future advanced systems. Planned development include automated shift planning supported by historical movement data, RFID-based RORO addressing for faster vehicle processing, integration of IBM's blockchain solutions for secure data exchange, GPS-based route optimization for heavy equipment, decarbonization initiatives aligned with sustainability goals. These next steps will strengthen Borusan Port's role as a technologically advanced and environmentally responsible smart port. Thank you for your attention.
Thank you for your presentation. Any questions? Seems no question. Thank you again. So we can move on to the next one. Barış Akush, are you here? Probably not here. Ertürk Erda,
Yes, I am here.
you can start.
Can you see?
Yes, it's clear.
Okay. Good morning, everyone. My name is Ertürk Erda. In this presentation, I will introduce an approach for detecting anomalies in IoT sensor data using NLP techniques. This study focuses on agriculture IoT systems and demonstrate how text-based representations can enhance anomaly detection. IoT ecosystems generate huge volumes of continuous sensor data, and this scale makes anomaly detection increasingly challenging. Traditional statistical or machine learning based approach mostly work directly on numerical value. Here I explore how converting these measurements into textual sequences enables us to leverage language models such as BERT. This transformation allows us to capture subtle irregularities that numerical methods sometimes miss, especially in domains like smart farming sensor deviations. This can have real-world consequences. The dataset used in this study contains nearly 38,000 agricultural observations, including environment parameters such as temperature, humidity, nutrients, and actuator states. These measurements represent a realistic smart farming environments with controlled energy use. The diversity of variables in the dataset makes it highly suitable for testing anomaly detection through language model behavior. To apply NLP models, each numerical attribute is transformed into categorical bins. Instead of raw values, we create interval-based tokens that describe the conditions of each sensor reading. When combined, these tokens form a structured sentence representing a single moment. This linguistic representation enables us to analyze sensor behavior using mask taken prediction. Distilbert is selected as the backbone due to this efficiency and strong contextual understanding. For deployment-oriented evaluation, the model is converted to ONNX format, generating both full precision and quantized versions. Quantization allows the model to run faster and with reduced memory, making it suitable for low power IoT environments. Classical perplexity cannot be computed directly in bidirectional transformers. I rely on pseudo perplexity. The idea is simple here. We mask each token one by one and measure the model's confidence in predicting from in main remaining context. High pseudo perplexity indicates that the reading is unusual or unexpected. This makes perplexity an effective unsupervised anomaly indicator. Two detection strategy used. First, labels the top 5 highest perplexity score as anomalies. The second relies on median absolute deviation. Using both methods helps validate the robustness of anomaly identification under different statistical assumptions. All experiments were conducted in a CPU-only environment on Google Colab Pro. I evaluated both the standard FP32 and integer 8 quantized versions. Quantization produced important gains. The model was reduced by percent 75, while inference nearly doubled in step speed. Despite these optimizations, anomaly detection outcomes remained almost unchanged. This demonstrates that quantized transformer models can maintain reliability even under aggressive compression. The distribution plots show that integer 8 result in slightly lower and more stable perplexity values. Both models show nearly identical anomaly counts when using a P95 threshold, while the method remains conservative due to tight variance around the median. Overall, the visual analysis confirms strong alignment between predictions. The results highlight that treating sensor data as text offers semantic advantage. Transformers can detect irregular patterns by interpreting relations between sensor reading the way understand language context. The success of the quantized model also open possibilities for deployment on microcontrollers and field devices, providing real-time anomaly detection with reduced computational cost. In summary, pseudo-perplexity-based NLP modeling is a promising alternative for processing IoT sensor data. Our approach shows that quantized models deliver comparable accuracy with substantial efficiency gains. In future work, I plan to incorporate labeled dataset, combine perplexity with supervised methods, and test the model directly on edge platforms such as Raspberry Pi. This advancement can contribute to smarter or more resilient agricultural IoT systems. Thank you for attention.
Thank you for your presentation. Any questions? There is no question. Thank you again.
You're welcome.
So we can continue with Fatih Baykal.
Merhaba, buradayım.
Merhaba.
Ekran paylaşıyorum. Görebiliyor musunuz acaba?
Evet, evet.
Evet. Merhabalar herkese, günaydın. Çalışmamız aslında hedef tespitiyle ilgili insansız hava araçları ve benzeri havadan yer görüntülemesi yapması gereken araçların daha önce tespit edilmiş bir hedef görüntüsünü koordinat tabanlı lokalizasyonun kullanılamadığı ortamlarda görüntü odaklı gerçekleştirebilmeyi sağlamak amacıyla e, devam edilmiş bir çalışma. Biz bu kapsamda aslında Loftier isimli bir görüntü eşleşme algoritmasının uygulamasını gerçekleştirdik. Burada daha önceden belirlenmiş, daha doğrusu Google Earth üzerinden ölçeklenmiş iki fotoğrafın hangi doğrulukta eşleştirilebileceğini, hangi irtifalarda, hangi açılarda, farklı açılar ve irtifalarda hangi sonuçları alabileceğimizi araştırmak istemiştik. Bu bağlamda aslında 1000 metre irtifayı temsil eden bir Google Earth görüntüsüyle daha geniş bir harita anlamına gelecek olan temsili bir harita görüntüsünü eşleştirdik. Bu çalışmayı aslında Nvidia'nın A100 GPU'su üzerinde, yani Google Colab ortamında yaptık. Kullandığımız algoritma aslında Local Feature Transformer olarak ifade edilen Loftier algoritmasıydı. Bu geleneksel görüntü eşleştirme algoritmaları olan Sift, Surf, Orb gibi çalışmayan, aslında CNN tabanlı bir algoritma. Görsellerin eşleşecek ve hedef görsellerin fine ve coarse özelliklerini çıkararak CNN üzerinden öz nitelik haritalarını elde edip bunları transformer tabanlı bir dikkat mekanizmasıyla eşleştirerek hem yerel hem de global bir bağlam ortaya koyarak eşleştirmeyi gerçekleştirmeye çalışıyor. Ama bu algoritmanın bazı problemleri vardı bizim için. Yani daha doğrusu irtifaya bağlı olarak ve eğime bağlı olarak farklı sonuçlar elde etmiş olduk. Temel olarak çalışma geliştirdiğimiz ortamda aslında hedef ve aranan görseli, harita ve aranan görseli tek bir şekilde, tek bir hamlede eşleştirmeksizin genel harita bölgesini taylara ayırarak parça parça gezip adım adım aslında bir arama yapmak istedik. Bu bağlamda işte farklı irtifalarda, yani aranan Google Earth hedef görüntüsü buradaki şu an gösterdiğim alanı temsil etmekteyken aranan harita görüntüsü işte 2000 metrede, 4000 metrede ve farklı eğim açılarıyla eşleştirme gerçekleştirdik. Burada şu görselde mesela ifade ettiğimiz kırmızı noktalar aslında bizim gerçek eşleştirdiğimiz ve ada eşleştirme arasında gerçek fotoğrafla eşleşmeyen mavi noktalarda artık yani eşleşmeyen noktalarımızı temsil ediyor. Dolayısıyla total potansiyel noktalarla gerçek eşleşen noktalar arasındaki oran bize eşleşme oranı olarak karşımıza çıkıyor ve bunları kıyasladık farklı irtifalar ve açılar için. Dolayısıyla aslında karşımıza irtifaya ve açıya bağlı olarak bir tablo çıktı. Bu tabloya baktığımızda aslında uydu görüntülerinin genellikle 0 ile 15 derecelik açılardan alındığı takdirde bir drone veya uçak için yüksek eşleşme gerçekleştirdiğini, fakat bunun üzerindeki işte 30 derece 45 derecelik açılarda eşleşme oranının düştüğünü ve optimum olarak da 2000 metre gibi açılarda bizim hedeflediğimiz yüksek, yani %90 üzerindeki eşleşme oranını yakaladığımızı, 45 metre 45 derece gibi yüksek açılardaysa daha düşük eşleşmelerin olduğunu görerek algoritmanın bundan sonraki çalışmalarda kullanılıp kullanılamayacağını değerlendirmiş olduk bu bağlamda. Teşekkür ediyorum dinlediğiniz için.
Teşekkür ederiz. Sorusu olan var mı? Yok galiba. Teşekkürler. So based on the list, there is no one left probably here. So we can end the session now. Thank you for your participant. Have a good day.
Thank you very much.
Thank you very much.
Thank you.